Let's consider the excess noise factor in an APD compared with a photomultiplier tube. An APD is really different than a photomultiplier tube in the sense that both electrons and holes contribute, whereas in the PMT, only electrons contribute. PMT has a single multiplication event that produces many secondary electrons, but in an APD, you only get one electron-hole pair per impact ionization. Where is this heading? It means that APDs have a higher excess noise factor than PMTs. So let's consider the case of a PIN APD out of a direct bandgap material. If we have light incident on this P+ contact, then essentially electron and hole pairs are generated by the light. The reverse bias sweeps the electrons in the intrinsic region to the N+ contact. And under this condition, only the electrons initiate the impact ionization. So it's a single carrier injection condition. However, if we have alpha equal to beta, so this is a case where essentially the secondary holes may also impact ionize on the way to the P+. And so if both carriers ionize multiple times during the flight, the device never shuts off due to the continuous regenerative process of impact ionization, and this can lead to avalanche breakdown. So if the hole ionization rate is 0, then the device shuts off with the last hole, and there's no feedback from the hole ionization, and there's no avalanche breakdown. And you can see this happening here, where on the left you see a case where you have both electron and hole impact ionization, and on the right you have no hole ionization. And so in the presence of the secondary ionization, for example, the hole ionization in the example above, the multiplication noise increases greatly. So for a fixed gain, there are fewer carriers present in the active region where the holes can ionize as well as the electrons in the case of compared with the case where the hole ionization equals 0. And so the statistical fluctuation is a lot more significant for a system with fewer carriers, and that leads to higher noise.